a new source of power at sea, capturing the energy of ocean waves and using that energy to generate electricity.
The whole idea here is to take a completely different approach to generating energy in the ocean.
An idea that evolved quickly at the University of Washington's Applied Physics Laboratory in collaboration with Columbia Power Technologies and the Monterey Bay Aquarium Research Institute.
Just a year ago, we had a concept, some sketches on the whiteboard. We didn't know quite what this thing was going to look like.
This thing is called WEBS, the Wave Energy Buoy that self-deploys. What it does is serve as a source of electrical power at sea.
As opposed to typical wave energy conversion devices, which are anchored to the seafloor and generate large amounts of power for sustaining onshore needs, this is all about having energy available in the offshore environment. There's no anchor, it's a free drifting system.
Okay, so this device here is a 1/7 scale model of WEBS. We have the surface expression up top here that has two floats, a central nacelle that actually has the power generating equipment inside it, and it's connected by a tether down here to a heave plate that's about 60 meters down in the water column.
University of Washington mechanical engineering student Curtis Roosh came aboard the WEBS project early to develop a model.
Paul sent along his drawings of a SolidWorks model of what the whole device would look like and a bunch of preliminary specs for what the different spring forces would look like in the device and all the lengths and weights and an idea of buoyancy. And I was able to take all of that and put it into the model and start running it at various wave conditions just to see if we were capturing a motion that looked reasonable.
As the waves pass by, the device operates by rotating the floats relative to the nacelle and the heave plate below. You can see that this yoke that sits underneath the nacelle maintains its position while the arms themselves rotate. And that differential motion of the arms is actually the rotary motion to the generators that gets passed through the gearboxes into the generators and actually creates the electricity that we use.
So this design is very unique. It's actually leveraging some core technology that private company Columbia Power Technologies has developed. So it's a direct drive wave energy conversion system. It has a power takeoff unit inside this main nacelle, which converts rotational kinetic energy that is basically brought out of the waves and then converts that into electricity on board.
Very tightly packed in here. You've got a generator here and a generator on this end.
The main electronics box here has the main computer system.
WEBS electronics and surface elements are tethered by cable to a submerged heave plate.
The heave plate, by remaining stationary in the water column, actually provides something for the surface expression to pull against. And because this is free drifting, this heave plate also has a significant impact on the hydrodynamics of the overall system. And we have to take this into consideration when doing modeling of how this thing will behave in the field.
Another aspect of the simulations was to see how this wave energy converter is going to actually move around given these wind, wave, and current forcings. And so we got an idea sort of which forcings provided the most push to the device, and then also how the power output of it changes as you let it drift or if you try to keep it in one location. Using a lot of these results from the simulations, we were able to better design the device and have an idea of what kind of loadings we're actually going to need to design for.
One really neat thing was that it actually qualitatively performed just like the simulation did. So this modeling that our graduate student did on the system really basically was spot on.
So this was a really awesome experience just in my first year of graduate school to be able to start with a project that's just in its earliest design phase, go through with modeling it, use that model to step forward and actually build a full-scale device, and then actually test it in the field and see how that whole process culminates in a device that produces electricity.
This system generated the exact amount of power we expected in that environment that we put it into, which was 106 watts of average power in a very small sea state. So to go from a year ago not knowing what this would look like to today having tested it in the field and demonstrating its performance is really a very fast-paced, exciting process to go through.
Mm-hmm.